Hello everyone, my name is Felipe Gonzalez. I am an assistant project scientist at the Department of Earth and Planetary Science of UC Berkeley, and today I'm going to present a new model that is based on Ab Initio simulations, and it allows us to understand how temperature increases during ramp compression. So our main motivation is to understand the physics that's behind ramp compression, which is this experimental technique that allows us to compress materials to extreme pressures, up to hundreds and even thousands of gigapascals. And these pressures appear naturally at the interior of exoplanets such as super-Earths, and it already has allowed us to observe new crystalline phases of different materials. Contrary to shock compression, where a shock launched into a material creates a new thermodynamic state of matter that is well characterized by the Rankine-Hugoniot equations, and where temperature measurements are often available, we do not have such equations for ramp compression. And as a matter of fact, temperature measurements are often not available in ramp compression. So we don't really know how close the ramp compression path is from the isentrope. All we know is that it's somewhere between the shock-Hugoniot curve and an isentrope. Ramp compression is available at leading national labs such as the Livermore National Laboratory and Rochester LLE, and it is the design of the laser pulse shape, whose power increases with time, that allows to compress these materials to these extreme pressures and densities, but without heating it as much as shock compressions do. Over the years, a number of ramp compression experiments have been performed on diamond that have taken this material up to 800 gigapascals in pressure, then up to 5,000 GPa, and more recently to 2,000 GPa. And it is the lack of temperature measurements in these experiments that makes it really difficult to assess what is the thermal state of diamond at these conditions, and whether we know the equation of state of diamond at these really high pressures, which would allow us to validate a number of models that have been proposed to explain the behavior of diamond at these extreme pressures. So a number of questions remain open. For example, do we actually know the equation of state of diamond at these conditions? How are we modeling the strength effects on what is the effect of plastic work on ramp compression? Are we following an isentropic path during ramp compression? And more importantly, what is the thermal state of diamond as is this ramp compressed? As I mentioned earlier, the shock compression can be characterized by the Rankine-Hugoniot equations, where the energy and pressure of the material can be obtained in principle at any volume and temperature from Ab Initio simulations. So in principle, we can do Ab Initio molecular dynamics simulations and obtain an equation of state of a material and solve the Rankine-Hugoniot equations. And thus we obtain the shock-Hugoniot curve that I show in this figure as the blue line. So basically we perform a number of individual simulations shown here in the yellow squares for a given isotherm, and we solve the Rankine-Hugoniot equations for that particular isotherm, which gives us a point along the shock-Hugoniot curve. We have successfully applied this approach in the past to predict shock-Hugoniot curves of different materials, and here I show you two examples. On the left you can see the shock-Hugoniot curve of magnesium oxide here in black, that you can see that it agrees remarkably well with two different experiments that took MgO up to pressures of 3,000 gigapascals in the pressure density space. Similarly, for MgSio3, our predictions are in very nice agreement with experiments here in temperature pressure space. So we would like to do something similar for ramp compression, and that's why we would like to propose the model that I am presenting here today. We published this model in this paper last year where all the details are, and here I'm going to present you a brief overview of how the model works. We rely on the idea that ramp compression should be similar to a multi-shock Hugoniot scheme in the following sense. Imagine that you have a single shock that takes a sample from an initial state of energy E0 to a final state of energy E. Then the area between the shock-Hugoniot curve and the line that connects these two states is basically the heat delivered to the sample. But imagine that you can break this shock into two, such that you take the sample to an intermediate state. Then the overall heat is reduced and we end up in the same final state of pressure but with lower temperature. So if we do this multiple times, we are approximating the ramp compression by a series of shock compressions, and this is what we will try to imitate in our simulations. We will start with a state of initial energy E0 that will be in hydrostatic equilibrium, and we will uniaxially compress the sample as the experiments do. So this state, uniaxially compressed state, will always want to relax to the hydrostatically compressed state, which means that the energy of this state is higher, and we will put that energy difference back into the sample to increase the temperature, and the temperature will be obtained as a result of this energy increase. Therefore, we start with an initial density rho A and temperature Ta. We compress uniaxially and hydrostatically to obtain the energy difference between these two states, and that energy difference is put back into the sample, which later on results in a temperature increase, which is what we are interested in. So once again, we start with an initial structure, compress at fixed temperature with uniaxial and hydrostatic compression, get energy differences that are put back into the sample, and we relax to obtain the temperature. Then that new state is used as the initial state for the next step in our model. So let me show you how our model works for 3 steps. We start with a density at ambient conditions, and we will go to 800 GPa in 3 steps. First from 0 to 200, then to 400, and then to 800 GPa. And this should overall decrease the final temperature, which should be lower than the temperature along the Hugoniot. And this is how it looks like. You can see here that in the first step it gets to a point very close to the Hugoniot, and then it immediately decreases considerably the temperature in the second step, and when we go to the third step and we get to the 800 GPa, we are at a temperature that is way below the shock-Hugoniot curve and more or less resembles an isentrope. Remember that here we're not imposing the Rankine-Hugoniot equations in our model, and we're not imposing that the compression is isentropic. We're just getting these energy differences between the uniaxial state and the hydrostatically compressed state. Now, how can we validate our model if no temperature measurements exist? Well, the next thing we can do is to compare it to an actual multi-shock Hugoniot scheme, and this is what we did. We took the equation of state of diamond that we generated from our Ab Initio simulations, which is a collection of different Ab Initio molecular dynamics simulations at different temperatures and pressures, and we used them to solve the Rankine-Hugoniot equations and derive the shock-Hugoniot curve. Then we take one point along this principal Hugoniot curve as initial condition for the next shock, and we solve the equations again to derive the second shock-Hugoniot curve. Then we do the same for a third, fourth, fifth Hugoniot curve, and the collection of all these points here are what we call the multi-shock Hugoniot curve. And when we compare this result with the model that I just presented, this is what we obtain. You can see that there's remarkable agreement between the multi-shock Hugoniot scheme, where the points are shown here in black squares, and our model that is based solely on the energy differences between the uniaxially compressed state and the hydrostatically compressed state. Remember that at no point we imposed that these points should satisfy the Rankine-Hugoniot equations, but they still agree with a multi-shock Hugoniot scheme. In addition, we also predict that the temperatures are below the melting line and well below temperatures that were predicted by Bradley et al. In this RAM compression experiment in a model that was based on plastic work estimates. In addition, we compare our predictions with a model that was published recently by Swift et al., where they use a Taylor-Quinney factor to account for plastic work, and our results point towards a Taylor-Quinney factor of 0.25 that agrees with the RAM compression path that we predict. This is the same model that was used in the most recent RAM compression experiments of diamond by Amy Lasicki et al. In 2021. Now, there are still some issues reconciling the simulations with experiments because there's a huge difference in stresses between the cold curve and the reported data. And for example, if we assume that the equation of state of liquid carbon and that the reported stress corresponds to the hydrostatic pressure, then the temperatures that we infer basically exceed 20,000 Kelvin, which is probably not plausible for these experiments, but it cannot be ruled out so far. We also tried to explain this data by high values of strain, where we basically did uniaxial compressions at constant volume, accommodating for the shape. And what we found is that not even with very high values of strain, we're able to access this error bar region of the data for a given density. We also tried adding porosity to the sample, but that only increased the difference between the reported stress and the average pressure that we have at these conditions. And to conclude, we have presented a model that explained how temperature increases during RAM compression that is consistent with a multi-shock Hugon scheme and also with a completely different model that uses the Taylor-Quinney factor to account for plastic work heating. We still have some discrepancies between experiments and simulations that have to be explained, but so far we have proven that the plastic work energies suggested in the aforementioned models are consistent with the energies that we are using in our model. So with that, thank you for your attention.